Hello everyone, and welcome to Introduction to R. In this lesson, we're going to be covering point estimates and confidence intervals. Now, to this point, this guide has focused on the functions and syntax necessary to manipulate and explore data in R. Data cleaning and exploratory analysis are usually preliminary steps toward the end goal of extracting insight from data through things like statistical inference and predictive modeling. So the remainder of this guide, this video, and all the ones that are going to come after it, are going to focus on methods for analyzing data and the tools for doing those analyses in R. Now, statistical inference is the process of analyzing sample data to gain insight into the population that the data was drawn from. In data analysis, we're often interested in the characteristics of some large population, but collecting data on the entire population may be infeasible. For example, leading up to the US presidential elections, it could be really useful to know the political leanings of every single eligible voter, but surveying everyone that can vote is not feasible. So instead, we might poll some subset of the population, such as 1,000 registered voters, and then use that data to make inferences about the population as a whole. So we'll start learning about statistical inference by learning about point estimates. Point estimates are estimations of population parameters based on known sample data. For instance, if we wanted to know the average age of all the registered voters in the US, well, since we can't sample every single person, we could instead take a survey of registered voters and then use the average age of those survey respondents as a point estimate of the average age of the population as a whole. The average of the sample is known as the sample mean. Now, the sample mean is usually not exactly the same as the population mean. This difference can be caused by many factors, including poor survey design, biased sampling methods, or just the randomness inherent of selecting a subset of people and drawing from that. We're not always going to draw people that represent exactly what the overall population is going to be. We're going to start by investigating this point by generating a population of random age data and then drawing a sample from it to examine what the mean of the sample is versus the mean of the population. So to do that in R, we're just going to start by setting a random seed that will allow us to generate the same numbers every time we run this. And we're going to start by generating the population. So this variable population ages is going to hold a vector that is going to be our population of people, and we're going to generate it using some random numbers from some different distributions. So we're going to have some exponentially distributed data and some Poisson distributed data. We're adding 18 to all these values so that all the voters are at least age 18, because that is a requirement, at least if you're in the United States. And then we're just going to go ahead and find what the average is, so the mean. We're going to save that and print it out. So let's generate this and see what we get as the result here. So the average age in this data set we just generated is 51.2 years old. So now we're going to take a sample from this data set and check what the average is again. So basically, we're going to set a new seed. We're going to take a sample from our population ages. The sample size will be 1,000 people. We'll save that as our sample. Again, we're going to take the mean, store it, and we'll print it out. And then we're going to also check the difference between our sample mean and the true mean by subtracting that. So we'll run that and see that the sample average was 52.16 years old. That's a bit older than the true average of the population. But since we drew a random sample, we just happened to get more people that were above average. Now, another point estimate that might be of some interest is the proportion of the population that belongs to some subgroup or category. For example, we might want to know what the race of each voter is in a poll to get a sense of overall demographics of the voter base. You can make a point estimate for this sort of proportion by taking a sample and then checking the ratio of the sample. So we'll give an example of doing that below by generating some new data. We're going to generate some new data called population races. It's just going to be a bunch of repetitions of different categories. So that's what we're doing here. And then we are going to take a sample from this data set. So our demographic sample is going to be a sample of 1,000 entries in this population. And the population has numbers according to what we generated here. So for instance, there are, what is this, 1 million people classified white, 500,000 Hispanic, etc. So the proportions we find in the sample, we'd expect to conform to the proportions that we set right here, but it probably won't be exactly the same because there is some randomness involved. So this for loop here is just going to go through each unique category and print out what the proportion was from our sample. So you can see here are what the estimated proportions would be for each group based on the sample data. So the white population, for instance, was estimated at 40%. I think that is actually exactly right. So we just happened to sample the right number of people from that category to get the right amount. But these other ones aren't exactly right. Like this proportion here should be 10%, I believe, and these ones should be 20, 20, and 10. So these ones we sampled a little bit off, but by sampling just 1,000 people, we were able to get very close to what the actual proportions were, even though 1,000 is way less than the total sample or the total population size of 2.5 million. So this brings us to the concept of sampling distributions and the central limit theorem. Now, many statistical procedures assume that the data you're using follows a normal distribution because the normal distribution has some nice properties like being symmetric and having the majority of the data clustered within a few standard deviations of the mean. Unfortunately, real data is often not normally distributed, so the distribution of the sample tends to mirror the distribution of the population itself. This means that if we take a sample from a population that's a skewed distribution, the sample itself is also going to be skewed or tend to be skewed in the same way as the population itself. We can investigate this by plotting some data that is skewed and then taking a sample from it and checking the skew. So to do that, let's make a histogram of the population age data we made earlier and also run the skewness function on it to check the skewness. And if we do that, we can see that the skewness is positive, so it has some skew, and we can see from, let me zoom out, we can see from the histogram here that the distribution is a bit skewed to the right. We would expect this to be a little bit more symmetric with less data on this rightward tail here. It's not very pronounced, but it's not exactly normal either. And if we were to do the same thing with the sample data we took, the skewness is very similar there, and we also see a histogram where there's more data at this upper end than we would expect from a normal bell-shaped curve distribution. Now, since our sample data has roughly the same skew as the underlying population, this suggests that any of those techniques that assume we're dealing with a normal distribution can't be applied to this data because our sample is skewed. It's not a normal distribution. But in reality, we can use sample data of this kind even in things that assume we're dealing with a normal distribution thanks to the central limit theorem. The central limit theorem is one of the most important results in probability theory and serves as the foundation for many methods in statistics. At a high level, the theorem basically states that the distribution of many sample means, known as the sampling distribution, will be normally distributed. This rule holds even if the underlying distribution you're sampling from is not normally distributed. As a result, we can treat our sample mean as if it were drawn from a normal distribution, even though the underlying population that it was drawn from might not be normally distributed. To illustrate, let's create a sampling distribution by taking 200 samples from our population and then making 200 point estimates of the mean. So to do that, we're going to initialize an empty vector for point estimates. We're going to draw 200 samples, and then we're just going to do a for loop 200 times, so for x and 1 to num samples. So 200 times we're going to do this. draw a sample of 1,000 from our population, and then store that in this point estimates that we're making. So we're basically making 200 different samples. We're making an estimate of the mean, and then we are saving it in this point estimate. So we're going to have 200 different samples with 200 estimates of the mean. And then we're going to take all of these estimates and make a density plot of it to see what the distribution of those sample means looks like. So this is going to be a plot of the sampling distribution. So when we plot that here, I might have to zoom out again, but we're seeing a curve that looks quite a bit more normal than the histogram we got before. We're looking at this right tail, and that doesn't look like there's a whole lot of extra data or skew at that point. The data pretty much just looks like one bump, whereas before we had quite a bit of extra data at this right end. So this is an example of the central limit theorem in action, and we can confirm this by running the skewness function on our new point estimates. So let's scroll down here and run skewness on point estimates. And we can now see that the skewness value is very close to 0. It's, for all intents and purposes, 0, and that's what it should be for a normal distribution. A normal distribution should have a skewness of 0. So by taking the sampling distribution, we took something that did have a decent bit of skew to it, a positive value, and we made it be essentially 0. In addition, the mean of the sampling distribution approaches the true population mean. So if we take the average of all of our point estimates and also check the difference between the average of those point estimates and the true population mean, we're going to get something a lot closer than we did when we only took a single sample. So if we run that, we can see that the average now is 51.2, and that is very, very close to the actual underlying average. So basically, the more samples we take and the bigger those samples are, the closer we're going to get to being able to accurately estimate the actual average of the population. So now we'll move on and discuss confidence intervals. A point estimate can give you a rough idea of a population parameter like the mean, but estimates are prone to error, and taking multiple samples to get improved estimates might not always be feasible. You might not have the time or resources to be taking 200 samples of 1,000 people. It's just not practical to do that. A confidence interval is a range of values above and below a point estimate that captures the true population parameter at some predetermined confidence level. For example, if you want to have a 95% chance of capturing the true population parameter with a point estimate and a corresponding confidence interval, you'd set your confidence level to 95%. Higher confidence levels result in wider confidence intervals, basically casting a bigger net around the sample mean you take that makes it more likely to capture the true population parameter. You calculate a confidence interval by taking a point estimate and then adding and subtracting a margin of error to create the confidence range. So the margin of error is based on your desired confidence level, the spread of the data, and the size of your sample. So if you know the standard deviation of your population, the margin of error is equal to this equation here, z times sigma over square root n, where sigma is your population standard deviation, n is your sample size, and z is a number known as the z critical value. The z critical value is the number of standard deviations you'd have to go away from the mean of the normal distribution to capture the proportion of data associated with your desired confidence level. For instance, we know that roughly 95% of data in a normal distribution lies within 2 standard deviations of the mean. So in that case, we could use 2 as our z critical value for a 95% confidence interval. This isn't actually exact. You can get something a bit more exact using the R functions for the normal distribution, and that would be Q norm. But for all intents and purposes, 2 is close enough for a 95% confidence interval. But let's go ahead and calculate a 95% confidence interval for the mean point estimate that we made for our population. So to do that, we'll start by setting a seed. We're going to say our sample size is going to be 1,000. Again, we're going to take our sample from the population with size equal to 1,000. We'll store our sample mean. Now we're going to get our z-critical value. We can do that with the qnorm function, or the quantile from the normal distribution function. We're actually going to use 0.975 for our 95% confidence interval instead of 0.95, just because when we're doing a confidence interval, we're interested in data both above and below the mean. So since this is going to be a two-tailed situation, we need 2.5% of the data on the top end and on the bottom end. So that's what this will allow us to get. And we're going to print out our z-critical value. And then we're going to get the standard deviation of our population. Since we actually generated that earlier, we can just do SD of the population ages. And then we need to calculate our margin of error. This is the amount we subtract and add to our point estimate to get the confidence interval. So our margin of error is going to be equal to our z-critical value, that was z up here, times the standard deviation. So that's the standard deviation of the pop, we already had that, divided by the square root of our sample size. So then we're going to store this margin of error, and the confidence interval then is just our point estimate, so the sample mean minus the margin of error, and sample mean plus the margin of error. So we're going to store the confidence interval as a two-length vector that's basically telling us the bottom and top end of it. And then we're just going to print it out. So let's run all this code, and it should do everything we need to do to generate a confidence interval. So you can see our z-critical value for the 95% confidence interval was very close to 2, but not exactly. It's a little bit less. And our confidence interval was 51.05 years to 53.27 years. So based on our sample, this is the range we'd expect the true population mean to fall within. If we remember earlier from the beginning of the lesson, I believe the actual average age was like just over 51. So it looks like this confidence interval does capture that true population average. Now we're going to proceed by generating several more confidence intervals and plotting them to get a better sense of what it really means to capture the true population average. So what we're going to do is just take several samples again. So sample size 1,000. We're going to save these results in intervals. We're going to do 25 of these. So we're basically replicating all the steps we did above 25 times, making 25 different confidence intervals. And then we're just going to plot them all so that we can see if they capture the true population mean in a visual way that will hopefully be easier to understand. So that's what this plot is going to do. You don't need to understand all the details of what the plot is doing here in terms of code, but we just want to look at what the result is. So you can see here in the resulting plot, a vertical error bar or interval has been drawn for every single one of our confidence intervals. We have 25 of them. And then the bold red line is a line denoting the actual population mean. So what it means to capture the true population mean is that when we draw the confidence interval, does the red line, the actual average, lie within the range of our interval? And to say we're using a 95% confidence level, that means when we make our confidence interval, there's a 95% chance that it's going to actually capture that true population mean. So we'd essentially expect that confidence intervals wouldn't capture the mean at about 5%, or at exactly 5% actually. And we can see that in generating 25 of these, all of them capture it except for one here. This one, for whatever reason, just randomly, the sample drew ages that were higher than normal, and the 95% interval actually doesn't capture the true population mean, so it made a mistake on that one. But you can see that most of them do, and as expected, about 1 in 25, it would actually be more like 1 in 20, but we actually got one of them that didn't. Now in this example, we used a case where we actually did know what the standard deviation of the population is. That's not always going to be the case though. So if you don't have the standard deviation of the population, you can use the standard deviation of the sample itself as a stand-in for the standard deviation of the population as a whole when creating the confidence intervals. The problem with doing that, though, is that the sample standard deviation might not match the population standard deviation, so you have to account for that additional source of error. To account for this error, we use what's known as a t-critical value instead of a z-critical value when we go about doing the calculation to find the margin of error. The t-critical value is drawn from what's known as a t-distribution, which is a distribution that closely resembles the normal distribution, but it gets wider as the sample size falls. So basically, when you have a small sample size, you're a bit less confident about your data, and you're going to end up with error bars that are wider as a result. So to give an example, this time we're going to take a new, smaller sample and then create a confidence interval without the population standard deviation, instead using the t-distribution this time. So to do that, we're going to take our smaller sample, so we're only going to sample 25 people this time instead of 1,000. We'll find the mean again. We'll use the t-critical value instead of the z-critical value. So instead of doing q-norm, so quantile from the normal distribution, we're saying quantile from the t-distribution. Again, we're going to use a 95% confidence level, so we want to cut off 2.5% at the top. The degrees of freedom, or DF, when you're using the t-distribution, is the sample size minus 1. So in this case, that's going to be 24. We'll print that out. Then we want to get the standard deviation of the sample. So instead of using the population, we have to use the sample itself. So we're going to get that there. And then the margin of error calculation is very similar to the one we did above. Instead of using z-critical value, we use t-critical value. And then we multiply it by the sample standard deviation instead of the population standard deviation. And again, dividing by the square root of the sample size. In this case, the sample size is a lot smaller though, so that's going to have an effect on the size of the error bars. Basically, this being a smaller sample means we're dividing by a smaller number, so this is going to result in a larger margin of error, and we're going to end up building a larger confidence interval. So let's see how that works. We're just going to take our sample mean again, plus and minus our error bar. Let's run this and see what our confidence interval is. The t-critical value, you can see here, is a bit bigger than it was for when we used the z-critical value. And when we look at the confidence interval itself, it's much, much wider than it was before. It goes from 43 years all the way up to 64 years. We know that the actual average is right around 51. The fact that it drew such a huge confidence interval compared to last time is based a little bit on the fact that this t-critical value went up, but we'd think that primarily this difference is due to the fact that we have a much different sample size this time. The sample size was only 25, so this square root 25 resulted in a much larger margin of error than when we're dividing by a square root of 1,000, which is a much bigger number, which would have pulled that margin of error down quite a bit. So this shows the importance of having a large sample size if you want to end up with a point estimate that has a pretty tight confidence interval where you can have a pretty good estimate of the true population proportion. You'd have to consider things like this when creating a survey so that you can get a good idea of the actual number of people you'd want to sample to come up with an interval that is tight enough for you to use in a useful way. Now, it should be noted that although we went through the trouble of calculating these confidence intervals by hand, in R, there are functions where you can do this sort of thing easily with a single function call. So to do that, you can use the t.test function here. So if we wanted to come up with the same confidence interval we just did, we could have just said t.test, pass in our smaller sample, the 25 data point one. If we run that, it'll do a little t-test here, and then it'll give us a 95% confidence interval, 43 to 64.3. Well, those are the exact same numbers we calculated above. It's just encapsulated those into an R function that makes it a lot easier to do. Now, earlier we also discussed making a point estimate of a proportion across different groups of a population. You can also make confidence intervals for point estimates of population proportions. So in this case, if you want to do a confidence interval for that, you use this different formula, z, so we have the same z critical value here, but the equation we multiply it by is a bit different. It's going to be the square root of p times 1 minus p over n. N, again, is the sample size, but p is your point estimate of the population proportion that you're dealing with. So for instance, if your point estimate was 40%, you just plug in 0.4 for p here, and then you'd calculate out the answer. So as an example, let's calculate a 95% confidence interval for the Hispanics group that we put into that data that we made earlier in the lesson. So to do that, again, we can get our z critical value in the same way we did before. Our point estimate p, I'm not going to scroll all the way back up, but it was 0.204, so a bit bigger than 20%, which should be the actual population proportion. And in that case, we took a sample of 1,000, so our n is going to be 1,000. Then we'll just plug all of these things into this formula. So z critical value times the square root of p times 1 minus p divided by n. That will give us our margin of error. Then to do the confidence interval, we just take our actual estimate, which was p, minus margin of error, plus margin of error, and that will give us our confidence interval. So we'll run that. So our result after running this is about 17.9% to 22.8%. So our confidence interval thinks that the true population proportion is in that range. Well, it is in that range because we know that the true proportion, the way we set up the data, was 20%. Now, instead of calculating this all out by hand, we could have used an R function to do this one as well. That function is called prop.test. For the function, you just need to specify what your x value is, so the number of observations that you had, and n is the total number of samples. So in this case, we drew a sample of 1,000, and 204 of those, so 20.4% happened to be the group we were interested in. So if we just call prop.test on those values, so the output is giving us a 95% confidence interval. It's basically the same as the one we got above. It might be a little bit different due to some numerical rounding and things like that, but it's essentially the same. So to wrap up with this lesson, estimating population parameters through sampling is a simple yet powerful form of inference. Point estimates combined with margins of error let us create confidence intervals that can capture the true population parameter with high probability. R's built-in probability distribution and testing functions make it easy to calculate confidence intervals quickly. Now, in the next lesson, we're going to expand on the concepts we learned in this lesson by learning about statistical hypothesis tests and the t-test. So thanks for watching, and I'll see you again next time.